So radioactive substances emit radiation. And this has been known for quite some time, more than 100 years. But they didn't know what it was. So they had to make up names. And since Greeks were the greatest original scientists, let's use some Greek letters. We don't know what this radiation is, but we'll call it an alpha ray. Here's the symbol for alpha. And then they found some radiation that goes a little bit further. Oh, we call that. Okay, we'll call it a beta ray. Again, they didn't know what it was. And then finally, they found some radiation that went a long distance, some radioactive substances that emitted radiation, and they emitted gamma rays. And they went the furthest. So scientists, of course, are curious people. That's their job. And they tried to figure out what were these things. And for some time, long time now, we've known them. And they aren't mysterious. We still have these names, and sometimes that makes people feel uncomfortable. Oh, it's radiation, it's alphas, betas, gammas, who knows what that is? Well, we do know what it is. Alpha ray is simply a helium nucleus. That's right, it's just simply 2 protons and 2 neutrons. If I could take a helium balloon and take the helium out, ionize some of it, like in a plasma, accelerate one of those helium nuclei up to a high energy, that's exactly the same as an alpha ray. Now, alpha rays do not penetrate very far, in part because they're a heavy particle. So this helium nucleus could be stopped by something as simple as a couple of sheets of paper, or your clothes, or enough air. Easy to stop. Here's a demonstration of a alpha emitter. You can see it's a lead-210 source. That's a particular isotope. And the lead-210 will change into mercury-206. And in that process, emit an alpha particle. Put this here. Okay, so you can hear that, right? And just by comparison, I have it over here. I'm not hearing an occasional gamma ray, right, or something, right, background. So that's lead. And I'll illustrate that, I hope, by taking this piece of paper, putting it here, and you hear many fewer clicks. You can watch here, you can see that it is easily stopped even by a few sheets of paper. What about betas? Betas are also something very commonplace in the subatomic factory. They are electrons. Just a simple electron. Electricity is moving electrons. An electron is what's stripped off of an atom when it's ionized. When they used to have cathode ray tubes, the old-fashioned thick TVs, they had an electron gun shooting at the screen. Those were electrons. A high-energy electron is a beta. And they do take a bit more to stop. Paper, clothes, air won't stop them, but they are stopped by some aluminum, maybe some thick aluminum foil, or certainly a thick sheet of aluminum, as illustrated here. Chlorine-36. Now, electrons go through a bit more. Here's the paper. Right? They're going right through paper. Let's try a piece of aluminum, like aluminum foil. There. The aluminum stops them. So I don't need the paper. I should just need the aluminum. All right. Hear that? Hear that? This particular beta source you see being stopped by the thin piece of aluminum is chlorine-36, a radioactive form of the chlorine molecule. Chlorine-36 turns into argon-36. Basically, beta emission is taking a neutron and it turns into a proton and an electron. That's beta decay. Finally, we come to gammas. Gammas are simply light. They're not light in the visible spectrum. Take a look here at the electromagnetic spectrum. You can see that we have this small little area, right? That is the visible spectrum, a very small range of energy that we can see. But if we go to a little lower energy, you get things like infrared or microwaves or radio waves, cell phone tower waves. That's very low energy electromagnetic radiation. Doesn't hurt you, doesn't ionize anything. We go up above the visible spectrum, you get to ultraviolet. That's how you get suntans. Going up a little bit more in energy, you can get up to X-rays to gamma rays. That's what we're talking about here. Gamma rays are high energy light. It's electromagnetic radiation. Right? Photons, high energy photons. And how to stop them? Well, you need some lead sheets. As this demo shows, some gamma rays, particularly the ones that come here from cobalt-60, are very energetic and take quite a bit of lead sheets to actually prevent them from getting through. So that's cobalt-60, and they're pretty energetic. If I take my paper, it has no effect. If I take my aluminum, it has no effect. If I take a piece of lead, some effect. Take a lot more lead. A lot more lead. Yeah, come on, we should be able to stop this. Anyway, lead will eventually stop it. That's already cutting it down, right? I mean, listen to that compared to that. All right, so we're definitely cutting it down. So these are the types of ionizing radiation. This is when something that's radioactive emits alphas, betas, or gammas, and then becomes some other substance. That new substance might also be radioactive. Eventually, it will emit more of these things and then become something non-radioactive, something stable. So you have all this. You might wonder, how do I make something radioactive in the first place? Many radioactive elements were formed when the Earth was formed. The potassium that's in your body, potassium-40 is a particular isotope. Very long, billion-plus-year half-life. It was created here when the Earth was created in the first place. Other things, humans have to turn into being radioactive substances. And you can do that with something else, with neutrons. Neutrons just don't run around all by themselves. But you can make neutrons in a nuclear reactor. And if I take a piece of cobalt and I stick it into a nuclear reactor where lots of neutrons hit it, it can turn it into the isotope of cobalt-60 that's now emitting more gamma rays. I put in chlorine there, I might be able to make some chlorine-36. I put in lead there, I might be able to make some lead-210. Things become radioactive when neutrons hit them, not when radiation hits them. And that's an important consideration. Many people say, oh, I don't want to be near something radioactive. I'm going to become radioactive. No, you aren't. Gammas, alphas, and betas might hit you, but that doesn't make you radioactive. All right, so let's just review what it takes to stop things. Alpha rays, a helium nucleus, is the shortest penetration. A beta can go through paper. It won't go through a thin aluminum plate. It's an electron. A gamma ray is just a high-energy photon, and you need something pretty substantial like lead to stop it. Now, on the same chart, you see neutrons. Neutrons only interact with the nucleus. And if you remember, an atom has this tiny, tiny nucleus, and almost all of it is empty space. So to neutrons, everything looks like empty space. You see here where it says water or paraffin. That's because they have hydrogen in them. Neutrons are hard to stop. Neutrons will only collide with the nucleus. And most of the time, if they hit a very large nucleus, they just scatter. They just bounce off and keep going. To slow them down, to eventually absorb them, to make them go away, you have to hit against something that's of similar mass. Just like if I took two ping pong balls and they hit each other, they both will end up moving. If a ping pong ball hits a bowling ball is not going to move. The ping pong ball just bounces off with as much energy as it had coming in. The things that are the closest to mass of a neutron is a proton, a hydrogen nucleus. So substances that have a lot of hydrogen, water is H2O, paraffin is some CH2 polymer, lots of hydrogens. That's what you need to stop and slow down and moderate neutrons. To make sure that you understand radiation, I'm going to give you the cookie problem. I got 3 cookies, 3 delicious cookies. All right, I've got a cookie that has alpha emitters baked into it. I have a cookie with beta emitters baked into it, and I have a cookie with gamma emitters baked into it. Now, you have to eat one. You can sit on one. And you can throw one out the window. So, I'm going to have my alpha, my beta, and my gamma. All of these have a half-life that's the same. Let's say it's something substantial, years, right? All of them have the same dose. All of them have the same energy. If you want to minimize your dose, obviously you shouldn't eat any of them, but if you have to, eat one, sit on one, throw one out the window, what order are you going to choose? What will be the best? So, take a few minutes, think it out, write down what you think is the best guess, and now let's logic it through. Let's talk about eating. If I eat an alpha emitter, every bit of those radioactive particles, the alpha rays that come off of it, are going to get stopped by my body. After all, a thin sheet of paper will stop it. Once I eat it, my body will clearly absorb that radiation. That means something could get hurt. When that alpha particle comes plowing through, it gets stopped by your cells. If it just gets stopped by the water, fine, it just warms it up. But maybe it gets stopped by the DNA. Maybe it changes something in the sequence of the DNA, and that could be very bad for you. So if I eat the alpha emitter, all of it gets absorbed in my body. That's not good. 100% dose. If I eat the beta emitter, same thing. A thin piece of aluminum foil will stop betas, 4 inches thick of person will stop betas as well. So if you eat the beta emitter, all of the beta energy will end up going into your tissue. Now, let's think about the gamma emitter. Gammas are hard to stop. If I eat a gamma emitter, some of those gamma rays are going to go right through me without touching a thing. And you say, no, how could that happen? Think about getting an X-ray. They put film behind you. They shine the X-rays, which are like gamma rays, through your bone. But some of the things get to the other side, and they actually expose the film. Some of those gamma rays went right through your body, exposed the film, and didn't damage a thing on the way. So if you eat the gamma emitter, some fraction, I don't know if it's exactly a half, but something less than 1, some of those gamma rays go right through your body and hit your neighbor, not yourself. So if you eat the gamma source, you're not going to absorb all the energy like you do if you ate the beta or the alpha. Okay? What about sitting on them? Alphas are stopped very easily. Even your clothes stop the alphas. Betas. Unless you're wearing thin aluminum pants, if you sit on the beta source, some will get you. All right? But this beta source, of course, is emitting, your cookie is emitting radiation in all directions. So if you sit on it, some of the betas are going to go towards the floor, not towards your body. So again, I don't know the exact fraction, but let's say it's a half. And it's the same thing with the gammas. All of these sources are emitting radiation in all directions. Right? So if they're emitting in all directions and you sit on it, some of the gammas aren't going to be pointing away from you. And those aren't going to get you. So again, maybe that's a half. Now finally, we come to throwing it out the window. And I guess it depends how far you can throw it, or on what floor you live on. But if you manage to throw it out the window, I'm going to assume you're throwing it pretty far away. 1 over r squared is wonderful. The further you are from this, the less radiation dose you can get from it just because of distance alone, let alone the wall, the window, the street, and everything else that you threw it through. So if you threw it out the window, you probably aren't going to get any dose from any of them. But here's the key. You got to eat one. You got to sit on one, and you can throw one out the window. Clearly, to minimize my dose, the eating column should be the gammas. Right? So here we have Cookie Monster's mouth, okay? And we are going to eat the gamma source. Sitting. Well, we got a 0. Let's sit on the alpha emitter. All right? We're going to sit on it. There we are. We're on our chair. And it's great because the seat of our pants, let alone the seat of the chair, will stop the alphas from getting through. Happy person. Okay. Finally, betas, they're the one that gets tossed away. And this is how you minimize your dose. You would eat the gamma, sit on the alpha, and throw the beta out the window. Of course, remember, I'm not advising that you actually eat radioactive cookies. That's what you need to know about radiation.